Now that we have talked about point estimators and reviewed some normal distribution properties and calculations, let's introduce the concept of a confidence interval. Along with hypothesis tests, confidence intervals are one of the two main items of study in inferential statistics. After studying this material, you should be able to answer concept questions about confidence intervals, including homework set problem number 3. Using a point estimator to estimate a population parameter always has an inherent problem. A point estimator, for example a sample mean, is a single number that varies from sample to sample. It is almost certain that the point estimator is at least slightly different than the population parameter. We don't have any measure of how confident we are that the point estimator is close to the actual target parameter, or a measure of how close it might be. Using a point estimator to approximate a target parameter is a bit like trying to hit a target with the tip of a dart. It will always miss by at least a little bit. Instead of just giving a single number, the point estimator, to estimate the population parameter, we give an interval of values centered on the point estimator to approximate the population parameter. This interval is called a confidence interval. For example, to estimate the population mean, mu, we use the confidence interval with some margin of error, e, and that confidence interval is the interval of numbers from x bar minus e up to x bar plus e. So using a confidence interval to try to capture a target parameter is more like adding wings to the tip of our dart. Even though the tip of the dart, the point estimator, will likely not be exactly on the target, the population parameter, the wings, the confidence interval, will likely capture the target. So in other words, the true mean is likely, we hope, to be somewhere in this interval. Even though x bar may not be exactly on it, we want this interval from x bar minus e to x bar plus e to contain the population parameter mu. So furthermore, with our knowledge of sampling distributions and probability, we can assign a level of confidence to this interval. For example, we might be 90% sure that our interval includes the true unknown value of mu. This actually solves the problems of just using a point estimator. So we're going to start by focusing specifically on constructing a confidence interval for the population mean. It will have a form x bar minus e to x bar plus e, and this is called a z-interval. It has a couple of assumptions. The assumption 1 is the distribution of sample means is normal. Now, is this a good assumption? Well, it often is. By the central limit theorem, it's a good assumption if the sample size is greater than 30 for any distribution. And it's also true for smaller sample sizes, smaller values of n, if the underlying distribution is close to normal. The second assumption is that we know what the population standard deviation, sigma sub x, is for the individual measurements. This is usually not a good assumption. We will later show how to use a t-interval if, more realistically, sigma sub x is unknown. Notice we're saying that we don't know the population mean. It's unlikely if we don't know that, we don't know the population standard deviation either. But it's a lot easier to explain this situation in the situation where we know sigma sub x. So that's why we're going to do this one first. Once we understand how to do a z-interval, and understand the concepts of that we're going to develop over the next few videos, then we can then generalize this to other situations. So let's do a setup here. Suppose we're interested in knowing the mean weight of all 7th grade boys in the United States. It's impossible to measure all of them, so what we can do instead is measure the weight of a sample of, say, 36 boys, and find the mean weight of the sample. Let's suppose it's 100 pounds in this case. X bar is 100 pounds. Now, by the way, this is hypothetical data. I don't have any really idea how much 7th grade boys weigh all together or what might be in a particular sample. But let's just go with this as an example. And we're going to be going with this same scenario over the next 2 or 3 videos. We know that this is the best point estimator of the mean weight of 7th grade boys in the U.S. is the sample mean of 100 pounds. So if we had to guess what's the population mean, we would guess 100 pounds. Now furthermore, suppose unrealistically, we know from history that the standard deviation in the weights of all 7th grade boys in the United States is sigma equals 12 pounds. So suppose we know this population standard deviation. We'll be using this example in the following several slides to help us develop concepts and formulas for a confidence interval approximation of the mean. So suppose that we are to take another sample of 36 weights from this same population of 7th grade boys. We would expect to get a different mean each time we take a sample, or at least probably vary a little bit. Hopefully all fairly close to the true population mean, but varying a little bit from sample to sample. So if we repeat this sampling over and over again, these sample means have a distribution of their own. Based on what we've done earlier in the course, can you answer these questions? What type of distribution does a set of sample means have? What's its mean, and what's its standard deviation? Press pause. Okay, now hopefully you can answer these questions. Since n is 36, which is greater than 30, the distribution of sample means is approximately normal, regardless of the distribution of the underlying weights of the population. In fact, weights have a tendency to be, for a group that big, a tendency to be normally distributed anyway, so we probably could have gotten by with a sample size of less than 36, but since the sample size is greater than 30, we don't really care what the distribution of individual weights is. We still know that the distribution of sample means is approximately normal. Furthermore, we know the mean of the distribution of sample means is the same as the unknown mean of the population of individuals. We know the mean of the x bars is the same as the mean of the individual x's. What's the standard deviation of the distribution of sample means? Well, remember that the standard deviation of the distribution of sample means is smaller than the distribution of individual values. Specifically, the sigma of the x bars is the sigma of the x's divided by square root of n. We are told that the distribution has a standard deviation of 12 for individuals, so that's a sigma of x, and we know the sample size is 36, so we have 12 divided by the square root of 36. Square root of 36 is 6, 12 divided by 6 is 2, and of course, obviously, this is contrived data to make everything work out really nice, but the distribution of individual values has a standard deviation of 12, but the distribution of x bar values has a standard deviation of 2. This is, of course, assuming we're taking sizes of samples of size 36 over and over again. If we also know that the distribution of individual weights is exactly normal, not really unusual for this, then we know that this distribution of sample means is also exactly normal. Suppose that, unknown to the people doing the sample, the actual mean of the population is mu is 101 pounds, and the individual weights are distributed normally. Remember, sigma is 12. Now, we're pulling back the curtain here a little bit, because remember, if we really knew that the mean was 101 pounds, then we'd be done. We know what we're trying to do is estimate this unknown mean of 101 pounds. But just for the sake of understanding what's going on right now, let's pull back the curtain and say we actually know the mean is 101 pounds, even though the researcher wouldn't know that. So let's take that information and draw graphs of the probability distribution functions, PDFs, for the distribution of the individual weights and the sample means of sample size 36 on the same axes. See if you can do this on your calculator right now. Press pause. Okay, now you're coming back after you've worked this yourself. You should have done this on your calculator. X is distributed normally with mean 101 and standard deviation of 12, where X bar will be distributed with the same mean, 101, and standard deviation smaller this time of 2. So we can graph those two PDFs with normal PDF on our calculator. here's how it looks on a TI-84. This taller, skinnier one is the distribution of sample means, has a smaller standard deviation of 2, where the larger standard deviation of 12 is for the individuals. The next page is the same graph. This graph is done by Minitab, and we can see these two things together. Remember that the distribution of sample means will have the same center but smaller standard deviation than the distribution of individual measurements, so the distribution of sample means is more concentrated near the mean. In the next slide, we're going to zoom in on the black graph, which is the one we want to be talking about, the distribution of sample means. So this red one, this shorter, fatter one, is the distribution of individuals. The sample means are going to have a tendency to be clustered up near the mean and more normal if the original one wasn't normal. In this case, they're both perfectly normal. And so we're going to take this black graph and redraw it on the next one, zoomed in a little bit. And that black graph from the previous slide is now the blue graph on this slide. So here's the graph of the PDF for the sample means, the distribution of sample means, i.e. the distribution of the X-bar values. This is the same as the narrower black graph from the previous slide. So to construct a confidence interval, we want to find an interval so that we are reasonably sure that our interval will contain the true mean. We begin by establishing what we call a level of confidence. That level of confidence is 1 minus alpha, which is the probability that the interval contains the true mean. So then alpha will be the probability that the interval misses the mean. So we want alpha to be small and 1 minus alpha to be large. We want a large level of confidence. So actually the level of confidence could be any number, but the usual suspects, the ones that you see used over and over again, are 90%, 95%, and 99%. Corresponding alphas are 10%, 5%, and 1%, respectively. Now, who picks this? Well, for many of the cases in the problems that you work for me, that will be something that's given in the problem. In reality, this is something that's decided on ahead of time by the researchers. For example, I've done both some research with a biologist and some mathematics education research. And in both cases, the industry standard there is sort of 95% for confidence intervals. So in all my papers, they've been used a confidence interval of 95%. But it wouldn't have to be. Other things might not need that high level of confidence, and 90% or even lower might be appropriate. Whereas if you're doing something a little more sensitive, like a drug test, you might want a higher level of confidence. 99% might be the level for that type of confidence interval. So for this example, let's use the 1 minus alpha's 95% confidence interval for mu. So the next several slides will show how the concepts and formulas for a confidence interval are derived. We want to start by finding an interval that is centered on and symmetric about the actual mean that corresponds to a probability of 95%. That turns out to be this red area that we have here under the PDF curve. That red area is has the same as our confidence level of 0.95. This interval is not the confidence interval, but it will have the same width as the confidence interval. So it's going to go from mu minus e to mu plus e. Now in the next slide, I'll show you how we got the 97.1 and the 105. But notice a couple things that we can see here. Notice that the red area is centered on the mean and has a value of 1 minus alpha equals 95% or 0.95. This leaves 1 minus that, or 0.05, for the unshaded area. But because of the symmetry of the distribution and the fact that this interval is centered on the mean and the distribution is centered on the mean, then the remaining 5% is equally divided into the two tails, leaving alpha over 2, which is 0.025 or 2.5%, in both the left tail and the right tail. Okay, the distance from the mean is down to the bottom is the margin of error. So this is mu minus E, and then this is mu plus E, for a total length of the red area, the red region, to be 2E. That's going to be the width of our confidence interval. Furthermore, notice that the probability to the left of this lower value, which we'll ultimately find out to be 97.1, is half of alpha. It's alpha over 2, or in our case, 0.025. The area to the right of this upper one is also alpha over 2, or 0.025. So the area to the left is 1 minus that, 1 minus alpha over 2, or another way to get that, 1 minus alpha over 2, which is 0.975. Another, maybe easier way to get that is to take the confidence level, add 1, and then divide by 2. So that'd be adding 1 is easy to something that starts at 0 point something, because now it's just 1 point that. So it's 1.95 divided by 2 is again 0.975, which is the area to the left of this, including the red area and the left tail. Well, why do we need the areas to the left of these? Well, that's because we want to use an inverse norm to find them. And that's exactly what we've done here. So notice if we knew ahead of time, we don't of course, that mu equals 101, then we can compute the values for the ends of the interval with a TI-84. Notice that 1 minus alpha over 2 is also 1 plus alpha, and then divide by 2, which is 1.95 divided by 2, or 0.975. This is the probability, the unshaded area under the PDF on the left, plus the red shaded area that's below the upper end. And alpha over 2, which is just 0.025, is the probability below the lower end. Another way to see that is it's 1 minus the confidence level, and then divide by 2. In any event, we use the inverse norm on the calculator to find these values. So it's inverse norm of 0.975 with a mean of 101 and standard deviation of 2. That gives us 104.91, which I think was rounded off to 105 here on the previous slide. And this 97.1 here is found by an inverse norm of 0.025, 101, 2. And that's the area to the left, the mean, and the standard deviation. That's about 97.1. The margin of error is the distance from the mean to either end of the interval, so that the width of the interval is 2e. In this example, the margin of error is 104.9 minus 97.1, and then divide by 2 is 3.9, at least approximately. So notice that there is a 95% probability that when we take a sample of size 36 and compute the mean of the sample, x bar, that x bar will be in this interval, the red portion, between this lower point and this upper point, between the 97.1 and the 100.5 in this red region. So there's a 95%, that is 1 minus alpha, probability that x will be in that interval from mu minus e to mu plus e. Now, we're going to turn this around using a little simple algebra in the next slide. So starting at the top here, we see that 1 minus alpha equals 95% is the probability that x bar is between x minus mu and mu minus e and mu plus e. So that means mu minus e is less than or equal to x bar, which is in turn less than or equal to mu plus e. Now what we want to do is turn this around so we put mu in the middle by itself. So to start that process, we're going to subtract mu from all three sides. That cancels the mu here and here, but puts a minus mu with the x bar in the middle. Next, we want to get this mu by itself, so we're going to subtract x bar to get rid of this. When we subtract x bar from all three sides, it cancels out the x bar in the middle, but leaves us a minus x bar in the front and a minus x bar on the last part. Finally, we divide by -1 to get mu by itself in the middle, canceling the -1. When we divide by -1, this becomes x bar plus mu e. This becomes x bar minus e, distributing the -1. However, when you divide by -1, it reverses the inequality from a less than to a greater than. Remember, when you multiply or divide both sides of a inequality by negative, it flips the inequality sign over. Taking this same inequality and just writing it from smallest to largest so that we can use less thans, we get x bar minus e is less than or equal to mu, which is less than or equal to x bar plus e, which says mu is in the interval from x bar minus e to x bar plus e. So, in other words, we're 95% sure that the x bar is in this interval from mu minus e to mu plus b, exactly when we're 95% sure that mu is in this interval from x bar minus e to x bar plus e. So, we are 95% sure that the mean is in this interval. Now, one thing you need to realize right now is that it's not the mu that's moving around. The mu is some fixed value. In our example, mu is the 101 pounds for the mean weight of all boys. That's not changing, okay? But when we take samples, different samples of size 36 7th grade boys and find their average weight, that's x bar. That's what's moving around. And so these intervals are moving around based on that. Actually, the widths are not changing because that was based on our confidence level. So, in other words, x bar is within e of mu exactly when mu is within e of x bar, which should make sense. So in other words, we're 95% sure that the sample mean is within e units of population mean exactly when we're 95% sure that the population mean is within e units of the sample mean. This interval in red here at the end is the confidence interval. That's what we're looking for. So, notice that there's a 1 minus alpha, or 95% probability, that x bar is in this red region. And this is equivalent to a 1 minus alpha, or 95% probability that mu is in this interval from x bar minus e to x bar plus e. This interval is not the confidence. It is the confidence interval for mu. It's not the same as this red region right here, but it has the same width. Okay, so we can see that here. Now, there's a problem with this, is we computed some of this stuff. We don't necessarily know what mu is. The nice thing about this is we can compute this without actually knowing mu. And part of that's because of the distribution of z-scores. We can standardize a distribution. So, since we really don't know the value of mu, we use the fact that we get the same area in a similar shape by looking at a standard normal distribution. Here we see the graph of a standard normal distribution where the red shaded area is centered on the mean. The red shaded area is the confidence level 1 minus alpha. The formulas below show the computation of the corresponding z-scores. Note that the z-scores for the mean is always 0, because it's the mean of the standard normal distribution, and it's also found as mu minus mu over sigma. Of course, mu minus mu is 0, divided by sigma is still 0. So the mean of the distribution of z-scores is always 0, the mean of the standard normal distribution. The z-alpha is a z-score so that there's alpha area to the right. Actually, and this is z-alpha over 2, so there's alpha over 2 to the right. And that value is going to be E over sigma of the x bars. Okay, this should be sigma of the x bars down here as well, but it still works out to be 0 regardless. And notice we get that because it's mu minus mu plus E. The mu's cancel, and so you just get E here. This one is mu minus E over sigma. When you subtract mu minus that, this turns out to be negative. Subtract mu from that, the mu's cancel, and you get minus E over sigma of the x bars. Okay, and this will be the z-scores. Well, how do you find the z-scores? We can find those with an inverse norm, and this gives us a nice formula relating sigma of the x bars, the margin of error, and the z-score, which we can find from a inverse norm. In our next video, we'll go on to see how to actually build the confidence interval from this, now that we know this basic theory behind it.